Hello, everyone. My name is Yue Fei, CTO and co-founder of uSens. And today, welcome everyone, and I will talk a little bit about inside-out tracking especially for the VR and AR applications. First, why we play games or why we use VR and AR. I think one of the main reasons is we want to do something that's infeasible to do in real life or too costly in terms of time or money. Everyone has a dream. Like my dream is explore the stars, go on to the moon. In VR, we can do that. And we want to do it in a way that's natural. We want to really walk around and touch the sandstones. And actually, that dream is shared by common people, not only gamers. Different age. So I think VR is for everyone, but right now it cannot reach everyone because of the tracking problem, interaction problem. So the problems are first position tracking and second freehand tracking without controllers. So how can we do that? One of the solutions is using inside-out tracking, everything integrated into the headset. What is hand tracking? What is interaction? First, let's think about how to classify different kind of hand-based interactions. If we look back in the past 1 hour, what did we do with our hands? So maybe we recognize someone we know before, so we say hi. So we use gesture to communicate information to the other person. So first category is gestural communication. Normally, the other side should be a person. We have tried some tests. If we do gesture communication to normal UI or machine type-like objects, people feel disconnected. People feel weird to do that. But if on the screen we see a person or some smart agent, people tend to do gesture interaction. And the second type of interaction, maybe in the past 1 hour, we pull out our cell phone and play with the cell phone, shake other people's hand, move the chair and sit down, or touch our own clothes, touch other objects. So that's direct manipulation, which means we have a direct contact with the object, and the shape, material of the object is pretty random. And how we manipulate that object is also high dimensional, is random. And the third type of interaction is interact via a tool. Like if we want to hammer a nail, we don't use the hand directly on the nail, but we pick up a tool to do the task we want to do. And for example, other things like in shooting game, we use guns. And in painting game, we pick up a pen and write in the air, like the toothbrush app. And so there are mainly three types of interaction. What kind of controller can allow us to do all of these three? And actually in the real life, we spend 90% of the time to do the middle one, direct manipulation, not indirect, not gesture communication. The normal controllers are more suitable for the third one because the shape is more designed to fit a certain tool, not all the tools, not all the random objects. So the other two types of interaction right now is not filled by traditional controllers. So if we have create another chart, so on the horizontal axis is how easy it is to carry this controller, and the vertical axis is how expressive this controller is, allow us to do the things we do in real life. Then the gamepad is somewhere here. It is okay to carry it around, but it cannot sense our natural hand expressions, and it's hard to learn. And how about 6-DoF controllers, like Vive's controller or touch? It is better at sensing our intentions, especially can track in 6-DoF. But it is harder to carry, including the setup is pretty hard. So how about the data glove? it is more expressive, but is even harder to carry and wear it. So there's another category is computer vision based 26-DoF tracking. So it is at that corner. It's very easy to carry, nothing to carry. And it's very expressive, can sense all the hand actions. And if we look at the hand, it is a soft body, very hard to replicate in the computer. But actually, it is driven by the rigid body bones, joints. So if we can recognize all the internal joints and the bones, then we can solve this problem. And using machine learning, we can do that. And today, we can not only do it on PC, but can also run it efficiently on mobile. So what the computer sees is the top left corner image, and using machine learning can recreate the bone structure in 3D. It can solve occlusion cases, self-occlusion, or two hands occlude each other, connect to each other. And hand tracking is only the first step. It is not interaction. It's not directly usable for games. So we need accurate physical interactions with objects. We also need to render it realistically in VR. So the next step is use the bones to drive a realistic hand model. And they use physics engines. For example, we can already use the physics engine in Unity to do some of the interactions without inventing special ones. And what people can do using this kind of interaction, and the next is an example. So now in the VR environment, people can see their hands, increase the feeling of immersiveness. And instead of touching the touchpad, for selecting something, user can directly point to the things they want. And instead of using the cursor or touch, user can directly pick up something or move it in 3D in the air. And also because we have more degree of freedom tracking, user can also turn it around, see the object in different angles. And the two-hand interaction as well. If people want to buy a watch, so everything is just more realistic, more efficient than other ways of interaction. But there are something we need to watch for, because on the mobile platform, the algorithm also using the CPU and may cause the CPU to downclocking, making the hand tracking slower, also rendering slower. So something we need to be careful. The algorithm already implemented a dynamic on-off feature. So when the hand is not there, it will go to a low power consumption mode. But also when designing a game, if there's some situation doesn't need hand tracking, it's better to turn it off to save power, to save CPU, keep CPU cool. And the other option is using the DSP, even a new ASIC to run this inside all the algorithms. And also range is an issue compared to handheld controllers, because when there's certain field of view of tracking device, when the hand is out of view, it's no longer being tracked. So some of the game may be not suitable for this kind of interaction. For example, ping pong game, people instinctively can wave the pad out of the viewing zone. Or some of the shooting game, people may use the gun like that. And another thing to help is in the game using visual and audio hints, tell the user now the hand is not being tracked. to have a smooth transition between tracking and a non-tracking mode. So the next topic is how about 6DoF head tracking. So nowadays, we know from inside out, there can be two ways to do head tracking. One way is based on some markers or reflectors. And another way is to do full SLAM tracking. So reflector or marker-based tracking, there are some pros. One is very low CPU consumption, and also very reliable. If user is looking at the range, the marker is placed. Compared to full SLAM, the pro is it doesn't need any setup, doesn't need to place the markers to a certain range, and there's no limit in scale. Right? So what's the cons of reflector-based? One thing is need to pre-set up. User need to buy the marker or reflector, need to place it in the room, and limit the scale based on how large, how far, how many markers or things people buy. But the full SLAM also has its issues. One is high CPU consumption. Also, depending on the environment, if the room is dark, it doesn't work. Or in the room, there's all white walls, it doesn't work. So how about first, a reflector-based SLAM? So here is a demo. If at least need 4 reflectors or need a barcode pattern, then the user can really look freely. Like this chess game, people can look closely to anything on the board, and the people can really walk around, see the chess game from his opponent's angle. So really change how the gameplay can be. Like the tower defense game, we can also design to be the user can move around, see it from all the angles. That would be much more interesting. And can run the hand tracking at the same time. So when we do full SLAM, we normally need RGB camera or mono cameras, just like a normal human vision. So it really adds, say, possibilities or into the gameplay. For example, we all know the mixed reality, there are 4 corners. One is reality. In the other corner, the lower right corner is virtual reality, means fully virtual, nothing real. But there are other corners, like augmented reality, means 90%, most of them is real, but a little bit virtual. And augmented virtuality means 90% is virtual, but there are some real elements can present in the virtual environment. So using the camera see-through kind of inside-out tracking to do the SLAM, at the same time can allow the VR device to operate in all the 4 corners. So I will show you an example, a demo of what that means and what the experience will be. But before that, let's go back. So I also said the interaction, we can categorize it into 3 types. Pure gesture interaction, direct manipulation, and the interaction with the tool. So the next demo also will show you the 3 types of interaction, how can they coexist in one application. So here, the position tracking is enabled by SLAM instead of Lighthouse. So people can look around, move around in a room scale environment. And everything in the room is interactable. For example, this a wind chime. Using the fixed engine, any part of the hand can interact directly with it. So this is direct manipulation. Right, user can also operate using the back of the hand. And this is a cup. User can grab it just like grabbing a real object. And one problem with the controller is when user open the hand, the controller will just fall off. It doesn't then the immersiveness will start to break. User need to remember, don't open the hand fully to prevent the controller from falling off. But freehand tracking doesn't have this problem. And how about interact with the tool? Using freehand tracking can still do it. User can grab a virtual pen and start to write in 3D. And how about gesture recognition? So based on this 3D skeleton, we can actually recognize many more gestures that can recognize by previous technologies. And here, user can do a zoom gesture and create a sun in this room. And using a different zoom gesture with different hand shape can create something different, like a cloud and a rain. Okay, so that's all about interaction, hand-based interaction. So what about mixed reality? So first, we'll show you an example of augmented virtuality. So in the VR environment, people want to see a little bit of real world, so can create a space portal connecting to the real world. And user can walk, not fully immersed in the real world. Now it's in the reality mode. Right? But some of the virtual object created, we can still hunt there in the real world. And then seamlessly, people can still transit from real world back to the virtual world, 100% VR. And now is another example of using hand tracking to do indirect manipulation, like holding a sword and play defense. And then user can go back to the real world. So as a summary of these demos, it shows hand tracking and position tracking adds interactivity. And it makes the feeling more natural to this virtual world. And it adds excitement into VR because people now can do augmented reality and a mixed reality. So as a company, uSens, we are developing both technologies. We're developing hand tracking, camera technologies, and position tracking. So what we provide on the left-hand side are the core technologies, and the right-hand side is VR and AR applications. So in the middle, we provide a SDK. It has a 3D hand model, can directly be used in your applications, and a set of predefined gestures. But you can also train your own gestures, and has physical interaction examples, assets, prefabs you can use. Also API for 6DoF head tracking, and also the feed to see the outside, stereo AR. So it supports Unity and currently runs on Windows and Android. So with in the future, after we improving these technologies more and more, maybe one day we can take more things off our wish list. Thank you. So, anyone has any? Yeah. Any questions? Hi, you first. Mm-hmm. Yeah, so the accuracy compared to Lighthouse, for example, the 6DoF position tracking, if using marker-based solution with about 10 markers, so first, the latency is higher than Lighthouse because even using the IMU, it's limited by the quality of the phone's IMU, depending on the hardware. But there's also solutions you can use a different IMU, higher quality IMUs, higher quality cameras, then I think will generate a comparable result. And for full SLAM, it is subject to the environment. When the environment is really optimal, it can achieve the quality, accuracy similar to Lighthouse, perceptually, only to the user. But from the data, we see still a higher error than Lighthouse. And for CPU consumption, yes, the full SLAM right now consumes too much CPU. It must use DSP or ASIC to assist better feature tracking. Because if you run the normal feature detector, the accuracy is not good. But if you run better feature detector, then the CPU consumption is too high. So that part needs help from ASIC.
Are you currently doing that, or working on that? Or is that
Yes, we are exploring all the different solutions. Yep. Yeah, I think if using the high quality IMU, for example, 1000 Hertz IMU, the camera may operate at a lower frequency, but the output is more depending on the quality of the IMU. So can also output more than 200 Hertz output. Mm-hmm, thanks. Hi, you're. Can you say that again? Okay, why? So the question is why I think data glove is not good enough. Maybe I haven't tried all the data gloves. I have tried some IMU-based or resistor-based sensing the bending. First thing, maybe the most important problem is it's very hard to put it on. The first, maybe you need to take 1 minute to put on properly. Then the user, the next step is need to do calibration. Not only per user calibration, but actually every time put it on, it's better to do some calibration because the position may be a little off. After everything is done, then the result, the best thing I have tried is pretty good. It can do 60 frames per second output. But the thing I have tried, although the frequency is good, 60 FPS, but it cannot sense all the fine finger motions. For example, for this finger, I see systems only can track one of the bone and only one direction, this direction, but cannot track other bones, cannot track this kind of interaction. So that's so far what I've tried. Yeah.
How do you focus to a more scalable, not only
So the question is how to track more body skeletons, not only the hand. So for body tracking, the technology was already pretty good in 2010, Kinect, using the outside-in tracking depth sensor to track the hand pose. I think the result is pretty good. But for inside-out solution, it's hard to have a system, a camera can see all the bones. So the solution can be using IMUs or still using Kinect or using magnetic sensors. And for the computer vision, machine learning point of view, the body tracking is easier. That's why people did it in 2010 using random forest algorithm. Because at that time, the algorithm and the computation power is enough to do body tracking. The body tracking, the complexity of pose is relatively simpler than the hand. Only 2 arms, 2 legs, 1 trunk is easy. But for hand, the occlusion is very bad, like a fist. The camera can't see anything, or like that. And the configuration, the self-occlusion is very hard to solve. That's why we start to see good solutions only in recent 2 years. Yeah, and the next battle is to make it run on mobile, power efficient, and very reliable. Yeah, next. So I guess the question is, how about using neural sensing, muscle electricity sensing hardware? Right, yeah. Okay, yeah, so for muscle electricity sensing hardware, as far as I know, I also tried it a few years ago. I mean, tried to develop the hardware and the algorithm. So the muscle signal does not tell us the current state of the hand. It only when hand change state, the sensor can pick up the delta. So it is very hard for that kind of system to reconstruct the current state of the hand. It can sense some of the actions, especially sudden action, then the signal is strong, but slow motion, the signal is weak. So it's good for something. Certainly it's very convenient to wear, but it's only good for very distinct, very sudden hand motions, and people need to learn, as far as I know. Right. Okay, so in that picture, I didn't show, I have the picture of 2-dimensional analysis. Maybe another axis should be haptic feedback. Right, so there's an issue with computer vision-based system, freehand system, that user doesn't really feel anything, the haptics. But the handheld controller also has haptic problem that the shape, the feeling doesn't really fit the real object. It only fits if I'm holding a pen, and if the controller, the shape is like a pen, I feel something is real. But if I'm trying to touch this surface using the controller, still it's wrong haptic. But at least it provides some haptic, and in certain games, if designed well, it's really good. And freehand tracking, there's no haptic. So, so my thinking is we have tried some prototypes. So if rendered scene is ultra realistic, then people, well, for pinching, grabbing is fine, because if the object is small, and when people pinching something, people still feel the object of 2 fingers touching each other. It's okay. On other things, need to heavily use visual feedback, sound feedback, even vibration on the headset to give people some feeling. Another option is still let user wear something to simulate the haptic. And also is the game design. If we design a thing that's not 100% realistic, but it's more sci-fi feeling of seeing, then people can feel that's okay, because that's a new world, not limited to the physics of the real world. And without haptic, also make people feel that people is more powerful, like I can pick up something with 0 weight. I'm so efficient. Then coming back to the real world is more like after swimming, coming back to the surface, feel, oh, everything is so heavy. So, so any more questions?
So today with market-based tracking inside out, what kind of latency are you seeing, and what's the latency currently on like a high-end mobile phone?
Can you say again? So latency of inside-out tracking system. Yeah, so far for the 6DoF head tracking, yeah, we already have something really good like the system in HoloLens. We haven't measured what's the real latency in the hardware, but looks pretty good. Should be below around 10 milliseconds. Yeah. And for hand tracking, since the processing is more complicated, latency is a little higher, maybe 15 to 20 milliseconds. Yeah, but the good thing is for hand tracking, since the hand is only occupying small part of the screen, so it doesn't really introduce dizziness if hand tracking has higher latency. Yeah. Can you say that again?
What kind of latency are you seeing for SLAM?
Right, so the question is what kind of latency we are seeing for SLAM. So for pure software-based SLAM, we see something around 20 milliseconds. And HoloLens heavily used special ASIC and with DSPs in the ASIC that helps feature tracking, at least I think feature detection part, maybe also helped other later stages in their SLAM algorithm help reduce the latency and the power consumption. Yeah, thank you. Thank you. Thank you.